So in this session, we will talk about how to enable high performance on VNFs. Everything is contained under a concept called EPA, or Enhanced Platform Awareness, which covers a group of techniques that are enabled in the NFVI, specifically in the servers, the compute servers that host the VMs, the virtual machines, or even some of them can be enabled in Docker containers as well. And these techniques are used to enhance the performance of network functions, because since we have NFV, we are being exposed to virtual machines that have a lot of requirements of performance, like throughput, higher throughput like than a regular VM, for example. And they consume more memory, more CPU intensive, because they are in the data plane many times. So this is a feature that in OSM, the feature that we are going to talk about is to have control of these requirements, of these settings from the orchestrator, from OSM. So if the VIM supports EPA, if it supports setting these techniques at the servers, which OpenStack does, then OSM will be able to orchestrate that. So some examples of the most popular enhanced platform awareness techniques are huge pages, CPU pinning, NUMA topology awareness, and SR-IOV. These are maybe the ones that are used the most. I think I have slides for each of them. In CPU pinning and NUMA topology awareness, what we are doing is controlling which CPUs our virtual machines are taking, not only at instantiation, but during its complete life cycle. For example, when you just launch a virtual machine without any EPA setting, these virtual machines will get instantiated in a random CPU. Probably it will be distributed among the different nodes, different cores in different sockets, and they will have access to memory that is in the different sockets, in the different nodes. So you don't have control of that latency that occurs between the core and the memory. Also, it will change over time, and it will be assigned CPU dynamically because the server constantly, or the hypervisor constantly redistributes the use of memory. So it won't have a predictable behavior regarding CPU consumption. And that's what is going on when we just launch a virtual machine. With CPU pinning and non-uniform multi-access topology awareness, what we do is pin a virtual machine to a specific core so that it's not changed, the core that is assigned is not changed over time. We can set a specific core with a number that identifies it, or we can just say, I want a dedicated core, and the VIM will manage that, and will assign the core, the hypervisor will assign the core, and then the virtual machine won't move from that location. Okay, that's CPU pinning. And then NUMA topology awareness is just making the virtual machine aware of the topology of CPUs. If you have 2 CPUs, if you have 4 CPUs, for example, you make the virtual machine aware so that you can say, I want this virtual machine to be located on one CPU only, so that all the cores, the virtual CPUs, are assigned in this particular node, and you can then ensure that those CPUs consume local memory. And you then are enhancing the performance of that virtual machine because it has less latency towards the memory. Then we have memory huge pages. This technique allows the VNF to request memory from a special pool where the way that memory is organized in pages is more optimal for bigger amounts of memory, and this enhances the performance too. By default, the memory, the RAM is assigned, distributed in 4K pages. So that's why we access the RAM and we can look for information. The way a huge pages works is that, and it applies better for VMs that have a lot of memory assigned. The way it works, is just increasing the size of the pages so that the system won't have to look through many pages to look for a certain information, let's say, to simplify it. In general, this has impact on CPU because it will spend less time looking for something. SR-IOV is another technique, and this technique applies to the data plane, specifically to the interfaces of the virtual machine. The way it works is that it assigns the virtual interface of the virtual machine directly to a virtual function or a virtual PCI of the NIC. So the NIC is virtualized and can be distributed to different or connected to different virtual machines. So virtual machines have access directly to the NIC, and it can have better performance because by default, for example, in OpenStack, we connect to either a Linux switch or an Open vSwitch, and we are subject to the throughput of that element, and that can make our machine perform at maybe 1 giga of traffic, 1 gig bits per second of traffic, and not more than that. There are other techniques like OVS DPDK, which can improve that, maybe 8 times better than that. But SR-IOV would take you directly to the NIC, and that means a near line rate performance. Okay, so there's another variation which is called pass-through. And pass-through, you just assign the complete NIC to a virtual machine so that it's used specifically for that network function. But SR-IOV allows you to share a single NIC with many virtual machines. Of course, you are losing some things by doing this because, for example, security groups are implemented at this element. I mean, next to the virtual switch, so you don't have any place to put security groups in OpenStack. Other things like local switching, of course, you won't have local switching between two VMs that belong to the same compute node. You will have to go out of the node and then back through the physical switching fabric to go to another element, even if it's inside the same node. So what is OSM adding to this? Because OpenStack already supports setting these EPA features to virtual machines. So open source MANO is there to abstract you from complexities, to let you model requirements of the VNF in a uniform way so that all your beans, no matter what version, no matter what type, if they are supported by OSM, they will model in the same way. In the case of SR-IOV, for example, when you set a net, you want to use it in OpenStack, you need to, besides setting the host for supporting this, which is common to everything, when you need to support SR-IOV, you need to configure the node for that. But then, once it supports SR-IOV, and you want to use it in OpenStack, you need to create a network assigned to the physical network that is already pre-assigned to the physical interfaces that will dedicate to SR-IOV. Then you need to create a subnet belonging to that network. Then you need to create the port and say that this is a direct type of port. I mean, it will go directly to the NIC. Then you will need to launch the VM assigned to that port. And for that, for each virtual machine that you need to support SR-IOV. And finally, when you have all your virtual machines that need SR-IOV exposed to the physical switches, you need to configure these physical switches for the connectivity of these VMs, because these VMs by default won't have a DHCP server, no, because OpenStack can't see them by default. You need to configure the networking in the outside part of the servers, so in the data center. And that could be, well, that's a very intensive, repetitive task that you would do just having OpenStack. So open source MANO provides some automation, and you just declare that your VM supports SR-IOV at certain network, and you do this once for each VM. Then you just, in the interfaces of the VNFs that need SR-IOV, you put that instead of virt.io or paravirt, you put SR-IOV. And that's it, you launch the network service. And OSM will take care of everything. Will take care of creating a network, will take care of the subnet, will take care of the ports and the VMs. And also, if you use the SDN assist feature, which I will explain later, OSM can even go to the switches and configure them, okay? So this is the way we support high performance, enabling high performance on VNFs. In our example, the place where we would want to do this is in this data plane. In the real world, we would do this at the data plane of the packet core, I mean interface that faces the node Bs, and the interface that faces the PNF, I mean the SGI, the Internet the SGI interface. So this is the data plane. In these two interfaces, in the real world, I would need to apply these techniques, for example, SR-IOV and the packet core for sure. If it's handling data plane, it needs to support a lot of throughput. Then we would use all these techniques together in this kind of VNFs. So in this example, we are configuring SR-IOV between these two ports, and so we are exposing these two VMs to the external world directly, and we have some physical switches outside that we control through the SDN assist feature. So what are the changes that we require to enable all these techniques? We have a property in the VDU called guest EPA. This is the place where you configure most of the features. For example, CPU pinning policy dedicated would mean that this machine would be assigned CPUs that will be fixed. Mem page size large would mean that this machine will use huge pages. So if the machine needs huge pages and there are no huge pages pool available in the servers, then the machine will not start. Okay, so that's why we need to plan this accordingly. Have a pool for huge pages, a pool for normal pages, if we expect the two types of virtual machines being launched at our servers. Then to enable SR-IOV, I just set the type to SR-IOV in the interfaces. So here we are enabling CPU pinning, huge pages, and SR-IOV. But when you enable SR-IOV, OSM assumes that it's a heavy a VM that requires a heavy throughput, so it will by default set CPU pinning and huge pages for you. Maybe this is not ideal because with modeling you want to have finer control, but for testing, for example. But in the real world, you would use all these features together. So that's why OSM is taking that approach. But maybe in the future we will support setting all of these independently. So it's just when you use SR-IOV. You enable this, and as soon as you enable this, you have huge pages enabled and CPU pinning enabled. And you can see it if you have not put it in the model. You won't see it, and you will have to know that it's asking for a huge page. So if you make a test at your labs and enable SR-IOV and just do that, make sure that your server supports huge pages as well. Otherwise, it won't start. Of course, you will see that at the Vim logs. Okay, so that's concludes this presentation about performance techniques. We will see an example in the next one, applying these techniques as well as SR-IOV and SDN assist.